Hi, good morning, everyone. In this session, we are just going to discuss an algorithm which can be used to find the shortest path between two vertices of a graph. So usually, we are searching for a shortest path from S to T. Usually, S stands for source and T terminal vertex. So in our step one, we assign a function, say lambda, and set the value of lambda of s equal to 0 and lambda of v equal to infinity for all other vertices. That's our step one. Then we set a current vertex, and in step two, we set the source as the current vertex. Step 3, we flag the vertex or current vertex as visited. So we flag the vertices which are being visited. Then in step 4, that's our iteration process. For all vertices which are adjacent to the current vertex, set the distance from the source to the adjacent vertex is equal to the minimum of present distance and the sum of weight of the edge from the current vertex to the adjacent vertex and the distance from the source to the current vertex. So that's given by the formula lambda of v, which we already assigned in step 1. Lambda of v equal to minimum of the current value of lambda of v and lambda of u plus weight of uv. So u is uh, the current vertex and v is a vertex which is adjacent to the vertex u. Then from the set of unvisited vertices, arbitrarily set in one vertex as the new current vertex, provided that there exists an edge to it such that it is the minimum of all edges from a vertex to the set of visited vertices to vertex in the set of unvisited vertices. And we repeat the process until all the edges been chosen or visited. So that this algorithm is known as Dijkstra's shortest path algorithm, and we illustrate how the algorithm is going to work using a simple example. So here we have a graph which contains six vertices, and they are named 0, 1, 2, 3, 4, 5, 6. Let's consider the vertex 0 as our source, and the vertex named as 6 is our terminal vertex. And so the vertex set, to start with, the vertex set of our graph G, uh, which can be represented by capital V, is equal to 0, 1, 2, 3, 4, 5, and 6. That is our terminal vertex. We are looking for the shortest path from 0 to 6. And now uh, you have to assign a value of lambda for all the vertices. So we can just tabulate them, the value of v and the value of lambda of v. So it's a table in which we give the values of v and lambda of v. So let's start with the vertices 0, 1, 2, 3, 4, 5, and 6. And the lambda of v value, as in described in step 1, the source vertex, for the source vertex the value is set as 0, and for all other vertices the value is equal to infinity. So this is the value, infinity. Okay, so that is our starting step, first step. Now we move on to our second step, set the current vertex to the source. So now for the time being, the current vertex of our calculation is our source, that is 0. This is our current vertex, and flag the current vertex as visited. So visited vertices are always being flagged. So flagged vertices can be formed as a set. So let us name the flag vertices are VF. So here the only vertex we visited so far is V0 or 0. Now for all vertices adjacent to the current vertex, so for all vertices which are adjacent to our current vertex, that is 0 in the given graph. Okay, I will place the graph somewhere else. This is our graph. Let us place the graph here. Okay. Now we move on to our algorithm. For all vertices adjacent to the current vertex, set the distance from the source to the adjacent vertices equal to the minimum of its present value and the distance from the distance and the sum of weight of the edge from the current vertex to the adjacent vertex. So for all vertices which are adjacent to the current vertex, that is here 0. So there are two vertices which are adjacent to the current vertex, that is 1 and 2. So for the vertices 1 and 2, we calculate the value of lambda using the formula minimum of lambda of u and lambda of u plus weight of u w. So we recalculate the value of lambda of u. So I just do it in the same table, or you can draw a separate table for each vertex. So here we recalculate the value of lambda of u, lambda of v. For the vertex 0, we just keep the value as 0 itself. For the vertex 1, since 1 is adjacent to the current vertex 0, the value of lambda is recalculated as the minimum of the current value of so I just write down the formula here. It is minimum of the current value of lambda for vertex 1, that is infinity, and the value of lambda for u, that is 0, that is 0 plus the lambda of weight of the edge from 0 to 1, that is 2. So the value is minimum of infinity and 2, which is 2. So the value is rechanged, or it is or calculated as 2. And the vertex 2 is also adjacent to the current vertex 0, and therefore the value of lambda is also recalculated for the vertex 2. The current value is infinity, and the new value is lambda of 0 plus lambda of 0 is 0 plus the weight of the edge 0 2, that is 6. So the minimum between these two values is 6. So the value of lambda is recalculated as 6. And for all other vertices, since they are not adjacent to the current vertex, it is treated as or it remains as the same, whether it is infinity or not. The value of that is not going to change at this step. So that is our first step or first iteration. Now we proceed this step further and recalculate the value of lambda by taking each and every vertex, or by visiting each and every vertices. So far we visited only the vertex 0. Now we have to choose a second vertex which is to be visited. So the process is simple. From the set of unvisited vertices, we have to choose a vertex. From the set of unvisited vertices, we have to choose a vertex. So there are unvisited vertices 1, 2, 3, 4, 5, and 6, and we have to choose a vertex out of this such as that the new current vertex, so which vertex we are going to choose from this, that is known as the new current vertex. And the new current vertex provide there exists an edge to it such that it is the minimum of all edges from a vertex in the set of visited vertices to the vertex in the unvisited vertices. So here we have only one vertex visited. From this visited vertices, and observe all edges from set of all visited vertices to the set of all unvisited vertices, and choose the edge with minimum weight. So here the minimum weight is there is only two edges from the set of all visited vertices to the set of all unvisited vertices, which are 0, 1 and 0, 2, and the minimum weight between them is 2, which is the weight of the edge from 0 to 1. So we choose 1 as the current vertex in our next iteration step. So 1 is flagged as the current vertex, and then we include 1 into the visited vertex, and then we recalculate the value of lambda again. Lambda of v is recalculated again. So the lambda of v for 0 actually it's not going to change because it is 0, so we can keep it as it is. But anyway, since the vertex 0 is adjacent to the current vertex 1, technically we can recalculate the value of lambda for 0 also, as it is the minimum of 0 and lambda of 1, that is 2, plus weight of 1, 0, that is 2 plus 2, 4. Minimum of 2 and 4 is equal to 0. So technically it's correct, but usually um, length of all the path is a non-zero value, and therefore we don't have to recalculate lambda value for the source. So now uh, one is our current vertex, and the lambda value of 1 is not going to change at this particular step. So the lambda of 1 is equal to 2. Then lambda value of 2. Now we are looking for all vertices which are adjacent to the current vertex. So there is only one vertex which is adjacent to the current vertex, that is 3, and we need to recalculate the value of lambda for the vertex 3 only. And for the vertex 2, the value remains as 6. For the vertex 3, it is the minimum of okay, it is the minimum of the current value, that is infinity, and the new value which can be calculated as the lambda value of 1, that is 2, plus the weight of the edge from 1 to 3, that is 5. So 2 plus 5, that is 7. The minimum of these two values is 7. So the lambda value of 3 is recalculated as 7. And since there is no edge from 1 to 4 or 5 or 6, the lambda values for those vertices remains as the same. So far we visit the vertices 0 and 1. Now we have to change the current vertex from 1 to a new vertex. So the unvisited vertices are 2, 3, 4, 5 and 6, and we have to look for the edges from the visited vertices, that is 0 and 1, to the unvisited vertices. So here the one with the minimum weight, there are edges like 0, 2, 1, 5. These two are the edges from the visited vertices to the unvisited vertices, and out of which the minimum one is from 1 to 3. So we choose 3 as our current vertex. So the current vertex status goes to the vertex 3. So this is our current vertex, and we recalculate all the values, or all the lambda values for the vertices which are adjacent to the vertex 3. So lambda of v is recalculated for all vertices which are adjacent to 3. Since 0 is not adjacent to 3, the value remains as 0. The vertex 1, we don't need to recalculate it. It is 2, since it is already been visited. And for the vertex 2, which is incident, or which is adjacent to the vertex 3, the value of lambda of 2 is recalculated as minimum of lambda of 3, that is 7, plus the weight of 3, 2, that is 8, and the current value of lambda of 3, that is the current value of lambda of 2, that is 6. Obviously 6 is the minimum value, so we are not going to change that also. The value of lambda remains as 6. Then for the vertex 3, again it is not going to change at this state. Then the lambda value for the vertex number 4, and 4 is adjacent to the current vertex, and therefore it is to be recalculated, and the value is uh, minimum of lambda of 3, that is 7, plus weight of 3 4, that is 10, and the current value is for the vertex 4 it is infinity. So the minimum value is 10 plus 7, that is 17. For the vertex 4 it is 17, and for vertex 5 it's again in adjacent to the vertex 3, so it is again the minimum of the current value is infinity, and the value of lambda of 3, that is 7, plus the weight of the h3 5, that is 15, which is 22. So it is 22, and the vertex 6 is not adjacent to vertex 3, so its lambda value is remains unchanged at this state. Now again we have to change the current vertex. Okay, so far we visited the vertices 0 1 and 3. 3 is the current vertex now. So these are the vertices which we have already been visited: 0 1 and 3. They are visited. 2 is not visited yet. 4 5 and 6, they are the unvisited vertices. Now find the shortest edge from vertices 0 1 and 3 to unvisited vertices. So the edges here are 3 2, 0 2, and 3 5, 3 10, and the weights are 15 10 8 6, out of which the minimal one is 6. It's from 0 to 2, so we tag 2 as our current vertex. So 2 is our new current vertex. This is our new current vertex, and the same process is going to be repeated. So the value of lambda is recalculated for all vertices which are adjacent to the vertex 2. So, and this 2 is added to the set of flagged vertices or visited vertices, and the lambda value is recalculated for all vertices which are adjacent to the vertex 2. So for 0, it is the current value is 0. For the vertex 0, the current value of lambda is 0, and the lambda value of vertex 2 is 6. 6 plus something is always greater than 0, and therefore it is not going to be changed. Then there's only one more vertex which is adjacent to 2, that is 3. So we have to recalculate the value of lambda for the vertex 3, and the current value is 7, and lambda of 2 is 6. 6 plus 8. 8 is the weight of 2 3. So 6 plus 8 is greater than 7, and therefore the minimum value is kept. So the value is 7, and for all other vertices the value remains as it is. So it is 2 6 17 22 and infinity. It is it's not minus, it is positive 22, and this is 17. Now that is our one iteration. So the current vertex status is now for the vertex 2 and is to be changed in our next step. So the vertices which we already been visited at 0, 1, 3, 2. 0, 1, 3 and 2. From here, unvisited vertices are 5, 4 and 6, and the edges which join a visited vertex to an unvisited vertex at this point of time, we have only two edges from 3 to 5 and 3 to 4. The one with minimum weight is from 3 to 4 of weight 10. So we choose 4 as our new current vertex. 4 is our new current vertex, and 4 is added to our set VF, and we recalculate the value of lambda for all vertices which are adjacent to the vertex number 4. So the value of lambda for V vertex 4 is unchanged at this step, and the value of lambda for the source remains as 0, and for the vertices which are adjacent to 4, for the vertices which are adjacent to 4 are vertex 3, vertex 5 and vertex 6, and for one is not adjacent to vertex 4, so it is 2. 2 is again not adjacent, so, and number 3 is adjacent to vertex 4. And observe one thing, the value of lambda for vertex 4 is 17, and the value of current value of lambda for vertex 3 is 7. So it's not going to change, because whatever may be the value of the edge or weight of the edge from 4 to 3, 17 plus that value is much larger than 7, so it's not going to change, so we keep the value of 7 there, 17. Then for the vertex number 5, vertex 5 is adjacent to vertex 4, and we have to recalculate the value of lambda, which is the minimum of the current value of lambda is 22, then 22, and the value of lambda for vertex 3 is 17 plus 4, 5. The H4, 5 has a weight of 6. So 17 plus 6, that is 23, which is more than 22. So its value remains as 22 itself. And for the vertex 6, and for vertex 6, the value of lambda of 6 equal to the minimum of the current value is infinity, and lambda of 4, that is 17 plus 2, that is 19. 19 is the minimum value, so it is changed to 19. So we got a value of lambda which is not infinity for the terminal vertex, but we don't know whether it is the minimal one or not. For that, we have to visit all the vertices of our graph. So the current vertex now is vertex number 4. Then The unvisited vertices are 5 and 6. So we have to find, or we have to check all the edges from the visited vertices to these unvisited vertices 5 and 6. And there are a lot of vertices like of weight 15, 6 and 2, and the minimal one is with weight 2. So 6 is the closest to the visited vertices. So we choose 6 as the current vertex. So six is the current vertex, and 6 is added to our set of visited vertices, and the value of lambda is recalculated for all vertices which are adjacent to 6. Here there is only two vertices which are adjacent to 6, that is 5 and 4. So the lambda value for 6 is 19. It is 19 here, and for the vertices which are not adjacent to 6, the lambda value is not going to change, and therefore these values remains as it is. And for 4 and 5 we have to recalculate, but for vertex number 4 the current value is 17, the lambda value for the vertex 6 is 19, so 19 plus something is always greater than 17, so it remains as 17 itself. And for the vertex number 5, the minimum between the current value is 22, and 19 plus the weight of the edge from 6 to 5, that is 6. 19 plus 6 is 25, and the minimum between 22 and 25 is 22. So the value here is 22. Remains as the same. Now the vertex 6 is added to the visited vertices list. Now the next step, so far there is only one unvisited vertex, 0, 1, 2, 3, 4, 5 is not visited yet. So from 5 we have to 5 we have 3 edges, and there are 3 vertices which are adjacent to the vertex number 5. Anyway, this all, as it is the only vertex, remains as unvisited. We have to mark 5 as our current vertex, and 5 is added to the visited list, and we calculate the value of lambda for one more time, and it's our last calculation of lambda, since the algorithm ends when all the vertices are flagged as visited. So this is our final set of values of lambda. Anyway, the value of lambda of v for the vertex 0, it remains as 0 since they are not adjacent to vertex 5. So it's 0. Vertex 1 it is 2, vertex 2 it is 6. For vertex 3, since vertex 3 is adjacent to the vertex number 5, the current value of lambda is 7, and for vertex number 5 the value of lambda is 22, and therefore the value is remains as 7, since 22 plus something is always greater than 7. Then for the vertex number 4, the current value is 17. 22 plus something will be greater than 17, so we can keep the value of that vertex also. Then for vertex number 6, again the current value is 19. 22 plus actually 22 plus 6 is equal to 26, which is very greater than 19. So the minimum value is 19, that is being kept. So this will give the length of the shortest path from the starting vertex 0 to the terminal vertex 6, and the minimum distance from the origin to the terminal vertex is 19, and we can trace the path in our given graph. Okay, look here. Since it is a small graph, we can trace it in the graph itself. The value of this is our track from 0 to 1, 1 to 5, 5 to 10, then this 4 to 6. This is our shortest path. This can be traced in a graph itself. If we have a large graph, then we have to retrace the path using the step itself. In that case, it is better to keep the trace of current vertices in each step and retrace the vertices which give the current value. Okay, for example, we start from the terminal vertex with weight 19, and the value of 19 is occurred at this particular step, and the current vertex at this particular stage is the vertex number 4. So this is vertex number 4, and the value of vertex number 4 is changed at this particular stage, and that is due to the current vertex at this particular stage is vertex number 3, and this is the value, and that value is obtained here when the current vertex is 1, and the value of current vertex become 2 when we have the current vertex as the source vertex. So if we retrace this path, then we can have the shortest path from 0 to 6. So this is how we find a shortest path in a connected weighted graph using Dijkstra's shortest path algorithm.